What's the benefit of understanding the internals of Compose? The one thing you could do, you could use Compose for other things besides UI. There are people that have built libraries on top of Compose, on the Compose runtime, and one of those libraries is called Molecule. The second thing is that what I'm going to share with you, a lot of it is undocumented. This is foundational knowledge that will really help you to understand, to attack like performance issues with Compose. So all the Jetpack libraries, all the source code for Android Studio lives in a repo called ASOP that you could check out. And the code that lives there is the runtime. Everything from the composer, the recomposer, all of the source code lives there. My name is Mohit. I'm a Google developer expert in Kotlin and Android. And my presentation is about Compose. And I'm going to go internally into how it works. I'm going to show you the API and the architecture of Compose. And all right, so let's start. So what I'm going to talk to you about is the architecture of Compose. And internally, there's something called a slot table, and I'm going to share with you how that works. I'm also going to share with you how recompositions work, and also going to show you how IR is generated. Before I start, how many people use Compose in production? Great. So you have a good base starting point. So you'll go underneath the hood, what's happening during initial composition and recomposition, what's that about? Before I start, I want to share that everything that I'm going to share is in my YouTube channel. I made this YouTube channel which has a playlist about how the compiler works, and you can check that out. Also have a playlist on how the runtime works, and everything that I'm going to share is it's on my YouTube channel. So before I start, I want to first talk about also another thing that I'm going to do. The second half of this presentation, I'm going to walk you through the code, walk you through the Kotlin source code about how it works. So what's the benefit of understanding the internals of Compose? So the one thing you could do, you could use Compose for other things besides UI. How many people use Molecule, the library? No one? Oh, one person. I'll take that. So Molecule is a library that's built on top of the Compose runtime. So what Compose is underneath the hood is just a way to be able to manage a tree of nodes. And what those nodes are, what they represent, could be dependent upon your use case. Could be the UI, or it could be your business logic. So there are a lot more use cases to Compose than the UI. So there are people that have built libraries on top of Compose, on the Compose runtime, and one of those libraries is called Molecule, which is used to set up your presenters, your business logic. This is an example of a library that utilizes Compose underneath the hood, which is setting up a state flow. So this is an example of using Compose in different use case. There are also examples of using Compose, for example, to build terminal apps. You could use it to also for server-side rendering. So there's a really good article by Jake, which is about the difference between Compose and Compose UI. And it talks about the nomenclature, it talks about how those two things are different. So I recommend checking out this article, which gives you a little bit of a history. So the second thing is that what I'm going to share with you, a lot of it is undocumented. This is foundational knowledge that will really help you to understand, to attack like performance issues with Compose. So first I want to talk to you about is the Compose source code. How is it structured? So how many of you know what Android open source project is? ASOP. Great. So all the Jetpack libraries, all the source code for Android Studio lives in a repo called ASOP that you could check out. And the code that lives there is the runtime. Everything from the composer, the recomposer, all of the source code lives there. So These are all the components that live in that size, in that repo. These are the components that you work with each and every day. So the second thing is the Kotlin source code. That represents the Kotlin repo. And the Kotlin repo, what it has internally is the Compose Compiler plugin. And what it does is that it takes your Compose code and it auto-generates a code to be able to hook into the runtime. So there's a purpose into the code that it generates. How many people have written a compiler plugin? One person, I'll take that. So a compiler plugin allows you to hook into the different phases of the Kotlin compiler. I'm going to walk you through at the end of this presentation on how that works in terms of live code it. So those are the different things. Those are the different transformers that transform your code to be able to hook into the runtime, to be able to hook into, for example, the composer. So this is a high-level overview of the architecture of Compose. When you look at this architecture, what you'll see is different components. And all these components have an API associated with them. They have a purpose on what they're going to do, and I'm going to share with you what that is. So I'm going to walk you through step by step what their API is and what the purpose is. So first, the most important thing to understand that the most basic level in Compose, the most basic data structure is called a slot table. The purpose of the slot table is to store information about all of the composable functions that you have. Their hierarchy. There's going to be a parent composable function. What is the child composable function? That's the purpose of the slot table, to store all that information to be able to update it during recompositions. So the slot table is the most important thing to understand, and the internal implementation is a gap buffer, which is used in editors. The question is, how does the slot table work? So how do you go about storing information inside of that table? And what is the information that's shared, just stored? So when you write your Compose code, you look at this, it's basically represented as a tree of nodes. You could have a composable function there, this calls another composable function there. So what you have here is a hierarchy, a graph, a tree. And you need to be able to store that information in some way. You need to be able to update it. When you change state, one of these nodes has to update. You have to do it in a way which is performant. So how does that work? So when you look at this, all of these different things, they're called groups. All your composer functions, what they do underneath the hood is that they build something called a group, which is a word which is synonymous with the word node. So how do you go about building these groups? That's what we're going to look at. So what groups do is that they track relationship between, we need to be able to track relationship between them. So let me give you an example. Here's the parent-child relationship. How do I track that? So these are the two goals. And we also need to be able to record any type of state that you have. So let me give you an example. Suppose you had a state like this, name right there, and one of these different composable functions relied on it. How do you track that information? Suppose those two nodes right there relied on that state and they need updating. How do you do that? So underneath the hood, in order to be able to build a slot table, there's a builder pattern that's associated with it. Let me back up and, client engineers, when they think about architecture, and I'm a client engineer, you think about architecture in terms of clean architecture use cases in that paradigm. In this paradigm, this is a different world. There are no use cases. This is like simple object-oriented programming. You have builders, etc. So it's a different way to think about architecture in this world. So the one thing, how do you go about building a slot table? When you declare a composable function in your app, you start your app, what happens? This thing gets executed. This thing right here creates a very simple empty slot table, which is a linear data structure in which it's going to store all the information about your composable functions. So what happens underneath the hood is creates a slot size, a slot table, 64 slots. Each slot there is going to store information about your composable functions. It's going to store in their state, any strings you're using, etc. Let me pause right there and back up. If you think about this, problem, this is a problem we're trying to solve. It's not about building an app. This is about you have an API, which is going to be your set of composable functions, and you need to be able to track that information. How would you go about doing it? This is one approach to do this. So right there, the next thing that you'll see is that this is a very simple example of creating a group inside of a slot table. Each group has a key. This is a very simple group. Start group and end group marks that information. So this could represent one composable function. So what happens is that underneath the hood, this will add in a group with a specific key. It auto-generates the key for you. So this is what happens underneath the hood. So now, when you go and add groups one by one by one, they all get stored in this linear data structure one by one by one. Now think about this. When a state changes, you click on a button in your app, you need to recompose a composable function. It needs to be able to traverse this linear data structure from the top to the bottom and to be able to update it. How does that happen? So when you add more and more groups, this is going to create more and more pages and add information to it. So the way you go about, here's an example of creating a group. And the next thing that I want to do is create a child group of it. Suppose you had an example where you had a composable function and it called another composable function. Those two composable functions have a relationship to each other. One is the parent of the other. How do I track that information? That information is tracked by group metadata. Here's an example of a group. This is a parent group with the key of 37, and it has a child group right there. So when you go in, you look at the slot table, it's going to add a group in the second slot. It's going to add them one by one linearly. How do you declare that there is a relationship between them? By specifying metadata. So what you'll see is that each group has information on what's the parent and what's the child. Now, in this world, information is stored using something called group addresses, which are hexadecimal values, binary values underneath. And this, like for example, 1 is the hex value for the child. So that's the metadata for that group. So suppose you had this right here, this node represents, that group represents that compose function, and you have a computed value of an integer. Where do you store that information? What if you had a string? Where do you store that information? Where is that information stored? So go underneath the hood. The way you store primitive values is by using the append method, and I'm doing append value of 1. It stores the computed value in your composition hierarchy. And what it does underneath the hood is that it's going to go and create another slot table just for primitive values. It's going to store a value of 1, and it belongs to the group 0. So you could store as many primitive values as you want. You could have a composable function that takes in not a single integer, but 2 integers. It's going to store them one by one right there. So you could also have a child group right there, which also has primitive values, and all of these slots are shared between all of those composable functions. So next thing is that, so you can see right there in the group metadata, each group has primitive slots that store information such as your integer values, your primitive values. They also store information about your reference types, such as the strings that you're passing in. So it looks like this. Suppose you had a string right there for this composable function. And what it's going to do is you could store it like this, starting like that. What it's going to do is that it's going to go into this slot table, and it's going to store it, and it's going to specify what group that is for. That's how information is stored for your composable functions underneath the hood. So the question now, when you look at this, you take a step back, you'll see each group has metadata, which is the primitive slots, reference slots. It also has more information in there. So let me make this important point. This is not accessible as, this is not an external API. This is an internal API. And you could go into the source code in Android X and the Compose runtime and play around with this. And I'll show you that at the end. So you could go and look at you could give it a composable function and look at what this looks like. There's a way to do that inside of Android X. So the next thing that we're going to look at is basically how do you go about reading a group. So right there, this is a very simple slot table with a primitive value of 1. There's a method called read. Where does this come into play? So when a recomposition happens, I have to go to the slot table from the top to the bottom, and I got to read each slot. And this API is used to do that. And what this API allows me to do is that allows me to go from the top, and I could go to the bottom, and I could grab information about the group. I could grab information about the key, the information that it contains about your composable functions. So then what I could do is that, so you could see I could also skip a group. This right there is what happens when recompositions happens underneath the hood. The generated IR code calls into this right there. That's how skipping is done. You could go from the top and you go to the top, you want to skip something because you don't want to update it. That's why recompositions are really important, because they give you performance. So the next thing that I want to share is that you could grab information such as group key and other information to it. So next thing is basically going to be, so the thing that creates the slot table, when you look at generated IR code, you'll see something called a composer that gets added to all of your composable functions. What's the purpose of that composer? Why is it added to every composable function that you create? The purpose of it is to be able to construct this slot table, to be able to record information about it. So now what I'm going to do is show you a practical example of what happens during initial composition. What do I mean by initial composition? Your app starts up. You have a list of composable functions from the top to the bottom. It has to go through each and every one of them. It has to be the most performant bottleneck in Compose is the initial composition, and that has to happen. It has to be able to track information so that you could do recompositions. So here's a very, very simple example of a composable function that you might write. And the question is, what happens underneath the hood when this gets executed, or what happens when you change that state right there? So this is something that's very, very simple. Let's start with this. There are 3 goals. One is to create the slot table that I shared with you. The next goal is to set up something called recomposition scopes. These recomposition scopes is very, very important. That's what everyone works with and looks at during recompositions. The next thing, you want to hook into something called the snapshot system. The snapshot system tells you when something changed and why it changed and what changed. And it's something that's really, really important. These are the underlying pieces of Compose. And what happens is that this is a library which can be reused. Compose can be reused for other things, the runtime. This library, Compose, has an entry point that you could hook into. Compose UI, Molecule, every tool that's built hooks into Compose. There's a pattern that's followed. Compose UI follows the same pattern, and it hooks into something called a composition right there, that composition object. It builds that composition object. If you worked on open source libraries, how do you build out the API? You either have a builder or you have some sort of type of initial API to start things up, and that's what that composition object is. So the next thing that we need to do, this is something that's really important. This right here is called the Recomposer. If you look at Compose UI, and every library sets up a Recomposer. This is the thing that drives recompositions that everyone tries to fix. This thing right here tells Compose, it starts to listen into why recompositions are happening, where it's happening, and you have to specify what you're going to do about it. So what this does is that it hooks into the snapshot system, and this is how it does it. It registers an observer. That change right there is what changes. So when you click on a button, for example, in a UI, and you want something to change, some composer function to recompose, that right there changed is the thing that's changed that caused a state change. And that change variable right there tells you what was changed. So the first thing that it has to do is set up that. Recomposer has states. These are all the different states that a Recomposer had. When you debug an Android app, you put a breakpoint. You could hook into the Recomposer and the info and look at this. So the next thing that to look at is that how do you listen to the stream of state changes on a Recomposer? This is how you do it. This is an internal API. So for example, when your app starts up, this Recomposer has an initial state. When a recomposition happens, it basically emits a different state in there. You can hook into this, listen into this. This is called the Recomposer. The Recomposer is the most important thing to set up when you're hooking into Compose. The next thing that you need to do is to set up the Recomposer, and by registering observer like that. The next thing that you need to do is to be able to set up a composition. This is the pattern which is followed by Compose UI and all the libraries. When you call set content underneath the hood, when you call set content in your app, that thing right there, what it does is starts the initial composition process on that composition object. I'm passing the Recomposer to it. This is the pattern. This is a common pattern for building on top of Compose. So what happens when you call that set content and you're executing this code? What happens is that there are specific transformers. So when you compile your code, when you take basically your Compose code, it gets translated into this right there. So what it adds in is a composer, and it adds in something called a change parameter. The purpose of that change right there is to be able to tell one composable function and another one what changed, what parameters changed. This right here, it also sets up something called a restart group. So what this is what it does underneath the hood is that it also sets up some logic to be able to skip your composition function. All of the body of your composition function is right there, right here. And it wraps around into this body, all of this logic, to be able to skip things. What it's doing right here is that it's hooking into the runtime. That's the purpose of this. This is what the compiler plugin does. So the next thing that you need to understand is that you also have logic in here to be able to skip a group like I showed you before. So when a recomposition happens, this thing right here gets executed, not this thing. And this thing right here is going to compute and go right here. So how is this code generated in the compiler plugin? In the compiler plugin, you have a set of transformers. They take your source code and they transform it. Why is this critical to understand? Recently, last week, Kotlin Swift export was announced. You're able to take Kotlin code and then export it to Swift. How does that work? Well, it builds on top of a concept called intermediate code representation. For that to work, something that was introduced called Swift Intermediate Representation. I could go over that at the end of my presentation if you want. And it builds on top of that idea. So that's why it's critical to understand that, how that Swift support was added. It was added on top of this. Well, these are transformers that take your code and they're able to generate different pieces of it, different pieces of that code. So in the end, what you have is this piece of code that it has to go through. So the first thing we need to do is to be able to set up our slot table. And we're going to start from here, called set content. And what this does is it tells the composer to build a slot table. This is the first thing that will get executed. It will restart a root group. In your app, when you look at the debugger, if you were to debug your app, set a breakpoint in the first composable function, you're going to find there's a root group that gets added with a specific key of 100. This is where that comes from. The next thing that it has to do when it sets up that group is to hook into your composable functions, and it does so like this. So it creates basically a group right there with the composable lambda. So this right here, set content, is a function type. And what it does internally is that it creates an instance of a class called composable lambda, which is a function type. And the next thing that it does, and this right here is important, invoke composable. This right here is the entry point into your code, into that code that gets generated. When that gets called, this thing starts to execute. When this executes, this is where the magic happens. It has to go in, it has to first create a restart group. 90% of your compose functions in your app will require a restart group. There's a way you could prevent from this code from happening. But you have to be very careful that it doesn't really produce bugs. What this does is this piece of code right here, what this does is that it goes in the slot table and it goes in there and to create a group as we saw earlier. So we need to create a group with a recomposition scope. And what it happens is that it creates a group, and inside there is going to add this recomposition scope right here. This is really, really important because this is the thing that drives recompositions in your app. What it does underneath the hood is that it has to remember the block of code that it needs to call when a recomposition happens. It also needs to store any state that it relies on. And this is a class that gets instantiated for your composable function. So, and it stores, for example, the state in there. And it has an API to be able to recompose, to be able to skip composition and validate it. The most important thing to understand, it creates an instance of that and it stores in there the group. What group does it represent? This is a key piece of information that it stores for recomposition. So next thing, it goes in and updates the values. So it stores the recomposition scope right there in the reference slot because it's a reference type. And that's where it stores it. So the next thing it needs to be able to do is store any computer types like that, like hello string, which gets stored in the metadata like this. So the next thing that it needs to do, the reason why we're doing this is that we could utilize this for recompositions. The next thing it has to do is to traverse down any other composer functions that you're calling, which is this. So it goes in, so these right here, you can see these other composer functions, both of them are creating these restart groups themselves. This is what happens in your app when you have one composer function that calls another one. It goes and traverses and builds a tree of groups. So in the end, when you execute this, in the initial composition, it looks like this. This is what your slot table looks like. And during recompositions, I need to be able to traverse down what change and update basically the reference slot for it. This has to happen in a very performant manner. It has to happen in a way which makes it performant to you as a client engineer. So the last thing that I want to talk about, those are the 3 goals. The next thing that I want to do is to now show the live code. What I'm going to show you is basically the source code for the Kotlin compiler, the Kotlin compiler plugin. So right here. Okay. So what repo is this? This is the Kotlin repo. This is the Kotlin source code. This right here has a hierarchy. Let me show you. Okay. So right there, we'll see on the left side is that it has a collection of plugins. The open plugin. Some of you might use that. It has the Compose Compiler plugin. The Compose Compiler plugin wasn't always here. So what the Compose code does is that it takes basically this piece of code, which is right there. Here's an example of a stable type that it's using. That right there. And what it does is that it has to transform it into this piece of code right here. So this is an example of a test in the compiler plugin. It has to generate this. The way you write tests is with unit tests, right? You do an assertion between what's expected and this is similarly, it's doing that. How does this code get generated? So here's an example of a transformer. This is a transformer, and this is called compose param transformer. Its job is to be able to do this. Its job is to be able to do just that right there, adding those two things in there. Those two things. How do you go and add those two things? Hook into the Kotlin compiler. Well, this transformer right here has something called visitor methods. So I'll show you an example of it. Let me here. So when you write compiler plugins, each transformer has visitor methods. So that right there is an IR. This is an IR type. Here's a thing to note, cool thing to note. With the introduction of Swift being able to export things, this was extended to Swift. There's also something called Swift IR. All the code right there goes through and looks at that function and it modifies that declaration and it adds in information. This API of what this does is not really documented. You have to go into source code and play around with this. So the last thing that I'll share, here's another example of, so here is something important to know. So this right here is a param state. When you have recompositions, this represents if it was changed or not. That's what this enum represents. This transformer is the most important transformer in the compiler plugin because it adds all the function skipping logic in here. For example, the param total count. So that's what it does. So the last thing that I want to share is that this API right here. So when you look at this, see this? See that right there? This is the analysis API. This was introduced in the K2 compiler. This right here, what it does is that it takes this source code right here, converts that, gives us semantic information. This part right here allows you to, this is utilized in the Kotlin Swift export tool, for example. This has a lot of benefits that it unlocks. So that right there is Compose. I'm very passionate about this, so I might be talking too much. So we have 8 minutes left. I want to open up to questions. I hope that was useful. I just want to add in one more piece of thing. So if you want to learn more about this, I have a set of YouTube videos which go into all this. And that's about it. I want to say thank you. I hope you learned something. All right, thank you.
Thank you, Mohit. Thank you so much. That was, I think it reshapes the idea I have of insightful. I mean, you really went deep into that, and I love that. It's like knowing how your car works after you've driven it for a couple of years, you know. So, do we have any questions from the room? The microphone is down there.